Howdy. This video is on the quantum mechanical description of electrons. Really small things like atoms and light behave very differently than larger things like apples. To understand small things like electrons and atoms, we have to use quantum mechanics. To understand atoms, molecules, and reactions, we have to understand electrons. After watching this video, you should be able to describe how electron orbitals are solutions to the Schrodinger equation, describe how there are an infinite number of solutions and hence an infinite number of orbitals. Each orbital is labeled with a unique set of three quantum numbers, n, l, and m sub l. Four quantum numbers, n, l, m sub l, and m sub f, labels each electron and atom. For each electron and atom, they'll have a unique set of those four quantum numbers. You should be able to describe what each of the four quantum numbers characterize and the limitations on their values. And given the four quantum numbers, determine what kind of orbital. And given the type of orbital, you should be able to determine what are the corresponding quantum numbers. So one question we could ask is, which of the following more accurately depicts the electron in an atom? Now, the one on the left is really pretty. It reminds people or makes people think about planets orbiting the sun, but it's really, really wrong. I consider it the Simpsons view of the atom. Remember, electrons are not particles, they're not like apples. They have a wave-like nature. And so to me, it's better to think about in terms of you have electron density around the nucleus. Unfortunately, in this depiction, the nucleus is way too big. Electron density is much bigger than the nucleus. And so Schrodinger applied the idea of electrons behaving as waves to the problem of electrons and atoms, and he developed what's referred to as the wave equation. It's kind of interesting. So Schrodinger developed quantum mechanics using wave equations. Heisenberg actually developed quantum mechanics using matrices. They both did this about the same year, and then the following year is found that their two formalisms were actually equivalent. And so solutions to the wave equation is a set of mathematical expressions called wave functions. Each wave function describes an allowed energy state of an electron. The position and momentum of electron cannot be known simultaneously. If you remember Heisenberg's uncertainty principle, that's why we have to talk about wave functions. And you should also remember electrons can be in a superposition of states. It doesn't have to be in just one state, but can be in multiple states at one time. So each wave function corresponds to an orbital, the region of space which an electron is found. The orbital does not describe the exact location. Remember again, Heisenberg's uncertainty principle, you cannot know the position and momentum simultaneously. Now, the wave function squared is proportional to electron density at a given point. But again, because there's an infinite number of solutions, there are an infinite number of orbitals. Only the lowest energy ones are actually filled. And so we only have to worry about the lowest energy orbitals. And so each orbital has a distinct set of three quantum numbers, n, l, and m sub l. And so you can think about n, l, m sub l kind of like being address. So that labels that orbital. So n is referred to as the principal quantum number. It labels the shell. So the first shell corresponds to n equals 1. Second shell corresponds to n equals 2. And it indicates the relative size. And so orbitals with n equals 2 are going to be larger than orbitals with n equals 1. L is the orbital angular momentum. It labels the subshell and kind of denotes the shape. And so we'll see that when L equals 0, that corresponds to a spherical shape. When L equals 1, that corresponds to a dumbbell shape. M sub L is referred to as the magnetic quantum number. It labels the orbitals in a subshell, and it indicates the orientation. And so I mentioned that L equals 1, you have dumbbell shapes, and the dumbbells will be along the different axes, and they'll have different M sub L values. Now, one important thing is their possible values. For n, it can go from 1 up into an infinity. Again, that's why there's an infinite number of orbitals. L, possible values for L depends on n. So L can go from 0 up into n minus 1. And so if n equals 1, L equals 0. If n equals 2, then L can be 0 or 1. M sub L values depend on L. And so M sub L goes from minus L through 0 to plus L. And so if L was 1, m sub L would be minus 1, 0, plus 1. If L was 2, m sub L would be minus 2, minus 1, 0, 1, and 2. And so the L quantum number defines the shape. And so I mentioned that for L equals 0, that corresponds to an s orbital, and that's spherical. L equals 1 corresponds to a p, and that looked kind of like a dumbbell. L equals 2 corresponds to a d, and that looks like a double dumbbell for most of those. And L equals 3 corresponds to an f, and those are a little bit more complicated. And so s orbitals are spherical, corresponds to L equals 0. And again, n defines the shape, the shell, and the bigger the n, the bigger the orbital. And so you can see here we have a 3s, that means that n equals 3, L equals 0, 2s, n equals 2, L equals 0, 1s, n equals 1, L equals 0, and so the 3s is bigger than 2s because 3 is bigger than 2.
The s orbitals are all spherically symmetric. Thus, contour plots connecting points of equal electron density are spheres for all values of the principal quantum number n. When n equals 1, the electron density decreases steadily with increasing distance from the nucleus. When n equals 2, the electron density goes to 0, then rises again to a new maximum. The spherical shell around the nucleus where the electron density is 0 is called a node. When n equals 3, there are 2 radial nodes. In summary, s orbitals of differing major quantum number have the same spherical shape, but differ in overall size and the number of nodal surfaces.
And so a node just means that there's no possibility of having electron density there. Now, one kind of interesting question we could ask is, okay, so psi squared is related to electron density. When you have n equals 2, you have a node. And so there's 0 electron density there. And so how can you have electron density on this side and on that side? Now remember, the x-axis is r from the nucleus going out. And so you can have these nodes just because electrons are not little particles. They have the wave nature. Little stuff is strange. And so L equals 0 corresponds to s orbitals. They're spherical. L equals 1 corresponds to p orbitals. They're a dumbbell shape. And like I mentioned before, one will be along the x-axis, one along the y-axis, one along the z-axis. Different orientations correspond to different m sub L values. Now you don't have to worry about which m sub L value corresponds to which orientation. L equals 2 corresponds to d orbitals. Most of these are double dumbbell shapes except for dz squared, which is a little bit more complex. And again, m sub L goes from minus L through 0 to plus L. So when L equals 2, m sub L is minus 2, minus 1, 0, 1, and 2. 5 m sub L values gives you 5 d orbitals. L equals 3 corresponds to f orbitals. The shape's even more complex. You can think about it as triple dumbbell shape. L equals 3 means m sub L goes from minus L through 0 to plus 3, so to plus L. So minus 3, minus 2, minus 1, 0, 1, 2, and 3. You got 7 m sub L values, 7 orbitals in that subshell. And so all the orbitals lie on top of each other. And please remember, these are volumes and not just surfaces. And so each orbital has a unique set of these 3 quantum numbers, n, L, and m sub L. And so in the first shell, that corresponds to n equal to 1. And so if n's 1, L has to be 0, because L goes from 0 up into n minus 1. And that would give you just that one s orbital. Remember, L0 corresponds to s. When n equals 2, L can be 0 and 1. L equals 1 corresponds to a p. And so in the second shell, you have an s and 3 p orbitals. Remember, if L equals 1, M sub L can be minus 1, 0, and plus 1. In the third shell, N equals 3, L can be 0, 1, and 2, and so that gives you SPD. When L is 2, M sub L can be minus 2, minus 1, 0, 1, and 2, so that's 5 d orbitals. And for the fourth shell, you can have SPD and F. Notice there are no p orbitals in the first shell, because again, L goes from 0 to n minus 1, and so if n equals 1, L can only be 0. There are no d orbitals in the second shell, because again, L goes from 0 to n minus 1, and so the second shell you can have L equals 0 and just L equals 1. So we can draw it this way as well, and so we have L 0, 1, 2, and 3. These are your possible M sub L values. Remember, M sub L goes from minus L through 0 to plus L. And so if we look at L equals 3, M sub L can be minus 3, minus 2, minus 1, 0, 1, 2, and 3. That gives you 7 F orbitals corresponding to the 7 different M sub L values. We can also depict it this way. So here's our first shell, our second shell, and our third shell. And again, L equals 2. That gives you M sub L of plus 2, plus 1, 0, 1, minus 1, minus 2, 5 d orbitals. Now we've talked about the orbitals. The electrons have a spin. The M sub S value can be a plus a half or minus a half. That corresponds to the relative orientation in a magnetic field. Now, it's unfortunate that we call it a spin. It just means the electron has a magnetic moment. And again, the electron magnetic moment can be aligned with the field or against the field. It was called a spin because it was discovered before quantum mechanics was completely developed. And so people believe that the magnetic moment of the electron is due to its spinning, and so they call it a spin, because according to classical physics, a rotating charged particle would have a magnetic moment. But the magnetic moment of particles, like electrons, is purely quantum mechanical in nature. The electron is not spinning. Now, M sub S can be plus a half or minus a half, so you have 2 possible values. And so every orbital in an atom has a unique set of 3 quantum numbers, N, L, and M sub L. Every electron in an atom has a unique set of 4 quantum numbers, N, L, M sub L, and M sub S. And so you can put a maximum of 2 electrons per orbital, one with M sub S plus a half, one with M sub S minus a half. So atomic orbitals, their solution to Schrödinger's equation. Every atom has an infinite number of orbitals, but we only have to worry about the lowest energy ones because only lowest energy ones are actually occupied. Each orbital is characterized by a unique set of 3 quantum numbers, N, L, M sub L. Each electron in an atom is characterized by 4 quantum numbers, N, L, M sub L, M sub S. According to Pauli exclusion principle, you can have a maximum of 2 electrons per orbital. And so please make sure you remember the possible values. N goes from 1 to infinity. L depends on the value of N, so it goes from 0 to N minus 1. M sub L depends on L, it goes from minus L through 0 to plus L. And M sub S is either plus a half or minus a half. So here's a question you can see in the very near future. How many electrons in an atom can have the quantum number N equals 2? Now, this could also be phrased, how many electrons an atom can be in the second shell? Remember that N denotes the shell, so N equals 2 would correspond to the second shell. Now, the other thing we got to remember is that while N can have values of 1 up into infinity, L can go from 0 to N minus 1, and M sub L goes from minus L through 0 to plus L. and m sub s is plus 1/2 or minus 1/2. And so if n equals 2, that means L can be 0 or 1. Now, if L is 0, m sub L is 0. If L is 1, m sub L is minus 1, 0, plus 1. And so L0 corresponds to an s orbital, so that would actually be 2s. And L1 corresponds to p. Remember, L0 is s, L1 is p, L2 is d, L3 is f. And so you have a 2s and a 2p. Now, if we think about the number of orbitals, you have one m sub L value, means you got one 2s orbital. You have 3 m sub L values, so that's 3 2p orbitals. And so we have a total number of 4 orbitals. Now it doesn't tell us how many, or the value of m sub s, and so you have a maximum of 2 electrons per orbital. And so 4 times 2 gives us 8 electrons for n equals 2, or the second shell. So again, there could be 2 in the 2s subshell, and there could be 6 in the 2p subshell. Each orbital can have a maximum of 2 electrons, one with m sub s plus 1/2, one with m sub s minus 1/2. Another question you could see would be how many electrons an atom can have quantum numbers n equals 2 and L equals 3. So again, n can go from 1 up into infinity. There's an infinite number of solutions, infinite number of orbitals, but only the lowest energy orbital is actually occupied, so we have to worry about it. L goes from 0 to n minus 1. Now it says that L equals 2, sorry, n equals 2, and L equals 3. Well, that's not possible. Right, so L is limited by the value of n. So if n equals 2, L can only be 0 and 1. So please make sure you remember what the limitations on these quantum numbers are. How many electrons in an atom can have quantum number n equals 4 and m sub L equals minus 3? And so again, n, 1 up into infinity, L, 0 to n minus 1, m sub L minus L through 0 to plus L, and m sub s is plus 1/2 or minus 1/2. And so if n equals 4, that means L can be 0, 1, 2, or 3. And then if we look at the possible m sub L values, so when L is 0, m sub L is 0. When L is 1, m sub L can be minus 1, 0, or plus 1. When L is 2, m sub L can be minus 2, minus 1, 0, 1, and 2. When L equals 3, m sub L can be minus 3, minus 2, minus 1, 0, 1, 2, or 3. And so it's asking us when n equals 4, m sub L equals minus 3. And so we got one orbital. And so that would give us a maximum of 2 electrons. Maximum of 2 electrons per orbital, one with m sub s plus 1/2, one with m sub s minus 1/2. Now if I had asked n equals 4 and m sub L equals 0, you notice you got 1, 2, 3, 4 orbitals, 2 electrons per orbital. The answer would have been 8. So how many electrons in an atom can have quantum numbers n equals 3 and n sub s equals 1/2? And so if n equals 3, then L could be 0, 1, 2, m sub L, when L is 0, m sub L is 0. When L is 1, m sub L is minus 1, 0, plus 1. When L is 2, m sub L is minus 2, minus 1, 0, 1, and 2. And if we just do the number of orbitals, and so for L equals 0, that corresponds to 1 orbital. You got 3 p orbitals, and then you got 5 d orbitals. And so that gives you a total of 9 orbitals. Now, if m sub s not denoted, or if m sub s is not stated, you'd go, okay, 9 times 2 gives me 18. But it says m sub s of 1/2. And so if m sub s equals 1/2, you can only have 1 electron per orbital. Right? So you can get 2 electrons in orbital because one can have m sub s plus 1/2, one can have m sub s minus 1/2. But if you say m sub s has to be plus 1/2, you can only get 1 electron per orbital, and that would give you 9 electrons. So this last one. So how many orbitals? You got to be careful if you're asked about electrons or orbitals. The last one we were talking about electrons. Here we're talking about orbitals. How many orbitals an atom can have quantum numbers n equals 4 and m sub L equals 3? And so if n equals 4, L could go 0, 1, 2, 3. M sub L 0, minus 1, 0, plus 1, minus 2, minus 1, 0, 1, 2, minus 3, minus 2, minus 1, 0, 1, 2, 3. And so it's denoting m sub L equals 3. And that would just be 1 orbital. And that would correspond to a maximum of 2 electrons. So again, please make sure you pay attention. Is it asking you for the maximum number of electrons or how many orbitals? So after watching this video, you should be able to describe how electron orbitals are solutions to the Schrödinger equation. There's an infinite number of solutions and hence an infinite number of orbitals. But again, only the lowest energy orbitals are filled, so that's the only ones that matter. Each orbital is labeled with a unique set of 3 quantum numbers, n, l, m sub L. Each electron in an atom has a unique set of 4 quantum numbers, n, l, m sub L, m sub s. So you can have a maximum of 2 electrons per orbital because m sub s has 2 possible values, plus 1/2 or minus 1/2. Please make sure you can describe what each of the 4 quantum numbers characterize and the limitations of their values. Given the 4 quantum numbers, you should be able to determine what kind of orbital it is, and if you're given a type of orbital, you should be able to determine the corresponding quantum numbers.